Hi everyone. So welcome to part two of the practice exam. And the first part was about the conceptual questions, and this is about the longer problems. So let's begin. And the second part says, this problem 6 says, consider a cone-shaped block. So we have a cone-shaped block submerged in two fluids. Okay, so there are two fluids, one on top, which is row 2, and one on the bottom, which is row 1. And the block has a height of 25 centimeters and radius 10 centimeters. Okay, so radius r on the bottom is 10, and the height is 25. So this is essentially 12.5 h by 2. This is also 12.5, and then this is the 10 centimeters. And the volume of a cone is also given to you, pi r square h by 3. So the question is, what is the density of this solid block in units of gram per centimeter cube? All right, so this is a classic buoyancy force problem because it's submerged and it's not falling or anything. So basically, we have done this in class that buoyancy force has to balance the mass of the fluid. So mg is equal to F buoyancy by fluid 1 plus F buoyancy by fluid 2. Okay. All right. And then what is the mass? Mass is rho of solid times volume of the cone times gravity. Then we'll have the first part, which is the rho 1 V1G, which is the weight of the fluid displaced. The weight of the fluid displaced. Fluid 1, this is fluid 1, and this is fluid 2. Weight of fluid 2 displaced. Rho 1 V1G plus rho 2 V2G, because that is the weight of the second. Note that you can also use gammas, but because this is given in densities, it's just easier to directly use densities times volume. But you can also use rho 1G as gamma, but clearly this is a density. We have given density, so we'll just use density. So the gravity gets cancelled. So I get, essentially I have to find the left hand side, rho s. Right? I know the volume of the cone. So what I get is, I get that rho s is equal to rho 1 v1 plus rho 2 v2 by v cone. Right, so this has been given. Now this is essentially what you have to find. Rho 1 v1 plus rho 2 v2 by v cone. Now, okay, so this is the formula. Obviously, if you do it until this point, you'll get some credit, but the main point is how to find further, right? How do I solve this? So the clearly the main challenge is we don't know v1 and v2. So we don't know we know the densities, the densities of fluid 1 and densities of fluid 2 phase, but we don't know the volume submersion fluid 1 and fluid 2. So from that perspective, let's do this think about this. So this is height and this is height. So this is fluid 1. Maybe just to clarify a little bit here, we're thinking about this fluid here, and then the second fluid is at the bottom, which is this one. So I don't know much about this problem other than the fact that these heights are same. So how do I go to get a volume now in the top fluid and the bottom fluid? One thing to note that this is also a mini cone. This is also a cone. If this height is h by 2 and this is h, because of similar triangles, you can imagine that the radius of this cone, so I'm basically calling this value as r1, right? So I know h1 is h by 2, right? I'm saying r1 will be also r by 2. Actually, better to call it rh2 than the second fluid. So this value I'm saying is h2, and then this is r2, the radius is r2. So what I'm saying is h2, because it's half submerged, it is h by 2, the total height by half. But by similar triangles, because it makes a triangle, a cone is like a triangle, the radius also is radius by 2, right? So in a way, we are saying that the volume of the second part, V2, is like a cone, because it is a cone, just a chopped off cone, half with half height, is pi r2 square by h2 by 3 by using this formula, right? And if we just plug in the values of r2 and h2, we will get pi r square h by 3 times 1 by 8, because everything is half. Radius is half, height is half. So essentially the volume of the top portion is 1/8 of the volume of the cone. So this is V cone by 8. Right? V cone by 8. And then the remaining value for the V1 is simply whatever remains of the cone. So which is 7 V1 cone by 8. So this also implies that V1 is 7 V cone by 8. 7 V cone by 8. So we substitute this value here. And then we just substitute this value by this value, because they both have the sum to V cone. Essentially, I get rho S is equal to rho 1 times 7 by 8 V cone plus rho 2 V cone by 8 by V cone. So this gets simply cancelled. Volume just drops out because it's a relative volume that becomes more important. So it is rho S is rho 1 7 by 8 plus rho 2 by 8. And so rho 1 is 8 grams per centimeter cube. And then rho 2 is 4. So this is 8 times 7 by 8 plus 4 by 8. So this becomes plus 0.5. So this is 7.5 gram per centimeter cube. So my rho S is 7.5 gram per centimeter cube. So hopefully this clarifies how to approach it. It was simply a buoyancy force problem. The tricky part being that appreciating that the top cone is also like top portion is also a cone, and that's why the velocity, the volume came out to be 1/8 by using the formula provided, and then that's it, and then you could get the answer. All right, so let's go to the next problem. So the next problem says, suppose a bathtub filled with water of density 1000 kg per meter cube with diameter 1. Okay, so this is the diameter first of the tub. So this is actually 2 meters. And then this part is 1 meter. This part is 0.5 meters. Just so that I understand the setup, is draining with the pipe with a diameter 1 meter, with the subsequently flowing into the diameter 0.5 meter. Okay, so water is flowing down, it's coming out, it's flowing like this. And then you may assume that points 2 and 3 are the same height. So the dotted line also indicates that. And that is 3 meters below. And so point 1 is at a higher depth. So that's why water is flowing because of gravity. And then the bathtub and the smallest pipe are exposed to atmosphere. So the pressure for, like at 1 and 3 are given to the pure atmosphere. The acceleration due to gravity is 10 meters per second square. Okay. So that's the setup. Density is given, gravity is given, height is given, and diameters are given. Okay, what is the velocity of water at point 3 and at point 1? Okay, so we have been essentially asked to find water at point 3 and point 1. So let's begin. So we can simply think of this as, okay, so there's only one stream of water flowing. So it's like, you know, it's not, water is not diverging into multiple outlets. So we can essentially use Bernoulli's first. P1 is rho V1 square by 2 plus GH. So I will use this height to be Z equal to 0. So this Z2 equal to Z3 equal to 0, and Z1 is equal to H, and this is equal to 3 meters. Okay. So I generally don't like to put the numbers right away. So I'll just keep it as H for a while. And then I have P2 plus, sorry, better to do it at 3, right? That's why the question is asking to 3. And rho V 3 square by 2 plus 0, right? Because the height is, um, um, sorry, by the way, it's not GH, it is rho GH or gamma Z. Sometimes I forget gamma H, okay. Gamma H or rho GH, okay. So this is what's been given to you, and that's it. So P1 and P3 are PATM because they are exposed to atmosphere. So we can cancel this out. The question is saying what is the velocity at point 3 and at point 1. So from that perspective, it makes sense to not assume it to be 0 because the problem did not ask us to do it to be 0. And so we can apply continuity equation to sort of further simplify. We know that A1 V1 is equal to A3 V3 is also equal to A2 V2 actually in this case, but we are still not at point 2. A1 V1 is equal to A3 V3. This is pi D1 square by 4 times V1 is pi D3 square by 4 times V3. So I get that V3 is equal to V3 is equal to there is a difference of 16 almost. So V3 is equal to it's 4 times difference, right? In the so V3 is equal to 16 times V1. Okay. So V3 is equal to 16 times V1. And so if I plug it, this is pretty because if it's diverging like 16 times, it's really like pretty significant. And then I can plug this back in here. Plug this back in, and we can say that this becomes essentially rho V1 square by 2. So then which is so V3 is 16. So I will do this a little bit so that hopefully this is clear. A little bit low a square is 16 square by 2 plus gamma H is equal to rho V3 square by 2. All right. And then if I take this on the other side, this becomes V3 square by 2 into 1 minus 1 by 256 equal to gamma H, which implies that V3 is equal to 255 by 256. Really, it's 2, and there is a rho as well, sorry, don't forget the rho. And so gamma by rho becomes G. So this is root 2 GH, which you have seen, 4 times square root of 255 by 256. Right, so essentially this is what you get in terms of your answer. And so let's put this into a calculator. So 2GH is 2 into 10 into height is 3 into 255 by 266. Actually, it's the opposite. My apologies. This is actually 256 by 255, not this way. 256 by 255. So 256 by 255. And we have to take the square root of that. So I will just find this number. And that comes out to be 7.76 meters per second. Okay? 7.76 meters per second. And then velocity 1 essentially here is 16 times smaller. So by 16, so it should be about 0.5, right? 0.485, 0.485 meter per second. All right. So the main thing that we're looking for essentially here is your ability to do the Bernoulli's theorem, apply it with continuity, simplify it to get the numbers for V3 and then also for V1. And that's really it. And then the second part of the problem is to measure the leakage. A flow meter is connected with a stationary liquid density ρ2 what is the value of H? This is a little bit more trickier side. So it's saying, what do you think is sort of this part, capital H here, and how do we find this number? So let's keep going. So first, why is there a pressure difference? So we know that at point 3, the velocity is higher than at point 2. They're at the same height, 2 and 3. So the kinetic energy is higher at point 3. So the pressure energy is higher at point 2. So it is going to be, it is because it's supporting more weight. So essentially, let's do it this way. What I'm saying is we have P2 plus rho V3 square, rho V2 square by 2 square by 2 is equal to P3 plus rho V3 square by 2. And what's the difference between diameters? It is 1.5. So we say pi d2 square by 4 d2 square by 4 v2 is pi d3 square by 4 v3. So v2 essentially becomes v3 by 4, right? So the diameters are half. So essentially what I'm getting here is P2 minus P3 is equal to rho V3 square by 2, rho V3 square by 2 times V minus into 3 into 15 by 16. So basically 1 minus 1 by 16, because I'm taking the square of this number. So it will be 1 by 16. So this becomes 15 by 16. So this is rho V3 square by 2 times 15 by 16. It's P2 minus P3. All right. So that is continuity and that applied. Now, I do know what the V3 is in terms of, or I can also plug in the value, but sometimes this is just my style. You can choose either. I do know what is V3, so I just sometimes find it easier to bring it back that way. So if I multiply that square there and put this, so I get rho times GH times 255 by 256 by 255 times 15 by 16. Okay. And the reason I like sometimes this is just to give me a feeling of the pressure and so on. So it's almost close to 1. I mean, so this is 16. This is rho GH times 240 by 215, 255. This is 48 by 51, so 16 by 17. So this is rho GH times 16 by 17. I believe that's correct. 16 by 17. Okay. So this is P2 minus P3. This is the value I have in terms of rho GH. Now, but this is not what the problem is asking. The problem is asking us to calculate capital H. And that's where I feel more of a practice can help you is you can do a more traditional approach of finding every single point and doing it, but we know essentially we're looking for how much extra weight this portion is supporting. So pressure here is higher. That is what we are getting. So this should be rho 2 minus rho 1 times GH of capital, right? So the extra weight, this is extra weight. This is the difference between the two points, right? This portion. So, and the left hand portion is supporting more weight because rho 2 is denser than the right one. So the difference is rho 2 minus rho 1 G times H, or gamma 2 minus gamma 1 H, because we are in densities here. So this becomes rho 2 minus rho 1 GH. So I see here this becomes rho 2 minus rho 1 G times H is equal to rho GH 16 by 17. And so nicely this cancels, G cancels. And by the way, this was row 1. So hopefully that's clear. This is row 1 everywhere. Before everywhere row was row 1, just to clarify, just take row 1, row 1, row 1, row 1, row 1, row 1 here, row 1 here, 1, row 1, Hopefully I didn't miss it too many places, but this was rho 1 everywhere else. And so this becomes, um, essentially, h becomes rho 1, rho 2 minus rho 1 into h into 16 by 17. So that's essentially the point. So rho 2 minus, so rho 2 is 5,000. So this is 1000 by 4000. So 1 by 4, so 4 by 17 of h. And I believe h was 3 meters. So this is essentially 12 by 17. So 12 by 17 is 0.70 or 0.71. So you can say 0.70 meters. 5 meters. Okay, so it is smaller than h because we are measuring the same pressure difference using a heavier density, but this is essentially the idea. And then the last page of this part B being repeated. So this is actually just that's it. So as you can see, we did two problems here, one on buoyancy and one on Bernoulli's theorem. Hopefully this was helpful. Again, you saw how I'm practicing this. And then, this will also hopefully help in exam. So yeah, that's it. And then all the best for your exam.